So yeah, and also feel free to stop me at any point in time if you feel confused or not, understanding something. Okay, so since we are recording, so you guys know that I'm going to cover the second half kind of content. I'm not going to focus on the first half. There may be some like tidbits or like themes from the first half, but nothing too major. I want you guys to focus on the second half content because it is quite heavy um, in terms of like difficulty. Okay, so as normal, like the previous review seminar, I'm going to start with true and false because true and false can be quite tricky. And I'm also going to make sure it's true and false with justification. I want you guys to be able to pull from theorems, kind of understand the construction of a lot of the concepts we covered in A37. Okay. So question 1, and let me know if you guys can't see. Question 1. If the series of AN is divergent, then for all C in the real numbers, CAN, series of CAN is also divergent. Is this true? False. Okay, and we have 1 vote for false. False. Hey, everyone is saying false. I'd like to see that. Okay. Guys, give me a color to write in. I know it's not important, but.
Do pink.
Do pink? Okay, you know what? Pink. We'll do pink. We'll do like a nice, like bubblegum pink. Cool. All right. So you guys are right. Perfect. Round of applause for yourselves. Whenever you're dealing with these existential quant or these like for all statements, you always want to consider few key numbers. 0's a big one. 1 is another one, and anything in between those. Those are typically where these for all statements break down, like really easily. So you always want to check 0 first. And you guys got it correctly. When C is 0, what is this series just going to equal to? 0. Cool. So the entire thing is just a bunch of zeros added up. Zeros added up indefinitely is still 0. So good catch on that one. This is just going to equal to 0. And 0 does converge. So C equals 0, edge case. Cool. Lovely. We're off to a great start. So this one is false. All right, question 2. Suppose the integral test can be applied to this series in particular. Then the series is going to be equal to the integral, where the function is equal to the summand. Okay. Why? We got 1 false. Oh, no one else? Okay, true. Okay, true. People saying true. Okay, so I'm expecting that people kind of get this, like, it's like a tough concept to grasp. Okay, people saying false. We're all saying false. Isn't it as n approaches to infinity? What do you mean? This isn't a limit. So it can't be as n approaches to infinity. Like the definition of sum and integral. Well, there is an infinity right here. Well, we're assuming that it can be applied to this one, right? Suppose that the integral test can be applied. So we have that we have that an is positive and we have that it's decreasing. So we have that. It's just rewriting of a series. Okay, this one's a tricky one. This one's actually false. Okay, and I'm gonna tell you why. It breaks down because of this. Notice, what is this? What's the definition? Like, what's our geometric definition or understanding of a integral? Area accumulated, area under the curve. Perfect. So let's just say that this is my function. It's a decreasing function and it's positive over its entire domain. Cool. Let's just actually do this. So it's, you guys can't yell at me. It's not defined at 0. So it's decreasing. It is area. Is this the same thing as adding a bunch of numbers, like specific, like if I were to take, oops, if I were to like draw this function, but keep it discrete. So like I'm just adding these numbers together. Is that the same? No, not at all. They're not related. The thing that is nice about IT is that it's a if and only if they converge or not. This series converges if and only if the function defined by the series or the sequence of the series converges, but they're not equal. The numbers that they equal to are not going to be equal. Hence, this thing breaks down. Cool? So this one is also false. Is there anyone that doesn't understand this or needs a better explanation? Be careful. This guy is an addition of just pure numbers. They are related by an inequality. The integral is flanked by 2 and 3 indexes. Yes. Wait, so this below statement is true. What do you mean the below statement? This guy right here is true. Yeah, if this guy converges, it's an if and only if this guy converges. Yes. This is a thing that we know by the integral test. The integral test tells us this. But we know it as this, like, if the integral converges, then we can say the series converges because that's more helpful to us normally. That's why we apply IT. But it's actually an if and only if. But turning an integral into a series is less helpful most times. So we just go the other way around. We turn series into integrals and then compute those. Cool? All right. If there's anyone that is confused by that, let me know. We can also talk about it near the end. Okay. Question C. Suppose the sequence of real numbers, if it's bounded for all naturals and the limit of an equals to 0, then we have that the series converges. Is this true or false? Okay, Faiza thinks true. Anyone else? Keep in mind, I tend to come up with really tricky true and false. I would say when it comes to true and false, stick with your gut until you're given a reason to doubt yourself. Okay, it has to be a very specific mathematical reason. So that'd be like things like thinking about counterexamples. People are saying true. Everyone's saying true. You're all wrong. Sorry. This one's false. And I'm gonna tell you why. Okay, I'm gonna give you a specific example, not AST. Yeah, Jonathan got it. Think about a classic example of a divergence. So if we're trying to disprove this, we want to think of something that the limit goes to 0, but it's divergent. The harmonic series is a specific example. An equals 1 over n. This goes to 0 as n approaches to infinity. Can we agree on that? It's also bounded from 1 to infinity. It's actually bounded for all the natural numbers, right? The vanishing condition is the contrapositive of this. Or not the contrapositive, it's the converse. I'll talk about what the vanishing condition is again, just for those of you who don't know it by name. Okay, but let's talk about why this fails, first of all. This guy, can we agree that it goes to 0 as n goes to infinity? Cool. So if it goes to 0, it's also bounded, right? This guy's also bounded for all n. And can we agree that it's a sequence of real numbers? Okay, so it satisfies the three conditions that we want. It's bounded, it goes to 0, and it's a sequence of real numbers. But we know that this diverges. This is our first example of a series that diverges in this course. It's our harmonic series. Whenever we're thinking about counterexamples, we always want to think about the simplest kinds of examples, the simplest forms of divergent and convergent sequences or series. Okay, does this make sense to everyone? Why this is false? Bounded is both sides. It is bounded by 0, it's bounded below by 0, and it's bounded above by 1. Right? Bounded means bounded from below and above. Okay, so the vanishing condition. No. Let's talk about it. Just because, okay, if this converges, then these sequence elements will go to 0. So an will go to 0. That is the vanishing condition. Essentially, what the vanishing condition says is that if you have a convergent series, the tail elements of your series go to 0. An is not the sum of all n. An is just a series or a series defined by a sequence. So an is just a function of n. So how is it bounded? Doesn't it go to, no, 1 over n does not go to positive or negative infinity. It's for n, the natural numbers. Plug in any natural number. It's the values that you get out are 0 and 1, because the natural numbers start at 1. They don't start at 0. Notice this. Does everyone remember the vanishing condition now? If your series converges, then we have that the sequence elements will go to 0 when you look at larger and larger n's. But that doesn't mean that this direction is also true. If it was true, we would have a very strong, very, very strong condition. We would have a very strong theorem here. But no, this is just a condition. But this is still useful. It says something about convergence, right? If we took the contrapositive of this, what do we get? You remember what the contrapositive is? The contrapositive is the not of this implies the not of this. So if we don't have, if we have that the limit of an does not approach 0, then we're going to have that, the series diverges. We like to think of this as another test for convergence or divergence. If you feel like your series diverges, compute its limit. See what it equals to. If it doesn't equal to 0, well, you have it diverges by the vanishing condition. Right? So this is what we like to call the div test or divergence test. Cool? So the vanishing condition is the first one, this one. And it's equivalent to saying the divergence test. The divergence test and the vanishing condition are equal. They're the same thing. The way that you prove the divergence test is just proving the vanishing condition. All right, can I move on? I'm gonna move on. Okay, so a lot of you guys from my tutorial will recognize Bob. You guys will recognize him. We've talked about Bob. Bob is really nice. The curved Bob is equal to an integral of this function is decreasing everywhere. Is this true or false? Are you guys talking in chat or no? Can't tell. Do we think this is true or false, guys? Just thinking. True? How do you test for decreasing? How do we test this? The derivative is negative. No, not n approaches to infinity. This is not a function of n. Yeah, in high school tells us that to find derivative, first derivative is negative, then that means that it's going to be decreasing over that interval. So how would you differentiate this? We want to find a derivative. How do you differentiate this? How do you differentiate, Bob? Not quotient rule. Bob is an integral. Yes, not FTOC corollary, FTOC. It's just FTOC. We can't flip the bounds. The bounds are, so do you guys remember this guy? Function of x is like, right, let's call this g of x. Function of t dt. This is FTOC. So notice the interior. Is it continuous over its entire domain? It's continuous over 0 to infinity, right? So the reason I called it Bob is to just get away from the fact that this capital F, we typically use it as the antiderivative. But here, this is not an antiderivative. This is not an antiderivative. And the reason I called it Bob is because a lot of us in the tutorial called it Bob. Exactly, it's a function. Bob is a function. But capital F we use as the antiderivative. So I'm not going to mislead you guys with that. You could also just, no, I'm not going to do that. So the way you differentiate this is you take whatever your function is, okay? You take your interior, the interior function, little f, plug in your g of x. In this case, our g of x is negative 2x. Then we're going to multiply by the derivative of g of x. So it's going to be an f of g times the derivative of g. That is what this is equal to. The derivative of an integral is just this. And in our case, it'll be this guy. Can we confirm that this is going to be negative everywhere? Yes, right? Just computing this part. My tutorial should have no issues doing this. We did a lot of questions using FTOC to find the derivative of an integral. FTOC is big. Make sure you know how to do this. The way to justify taking the derivative of an integral is to find if where this is continuous. This, notice it's going to be continuous over 0 to infinity, right? So FTOC allows us to differentiate integrals. The corollary of FTOC is your capital F of B minus F of A. This is FTOC corollary. The fundamental theorem of calculus. This is really big. You guys should know this. Like, this is super big. You can find derivative of integrals. Yes. Okay, does this make sense? If you guys can confirm that this, whatever I have written here, is negative, then you're good. This is true. I expect that you guys should know how to do this because there were so many practice questions. F would be the little f inside your integrand. It would be the thing that is in your integral. Reason that I don't use capital F here is because it's not necessary to use capital F. Capital F is just a placeholder. You can call your function whatever you want. I would suggest doing a lot more practice on questions like these. Are we good for this? Cool. All right, let's move on. This definite integral is equal to 0. Is this true or false? Okay. Yeah, you guys got it. So notice the bounds. I even put definite in front of it just to remind you guys of that fact. Notice the bounds are one is a negative of each other, of the other. When you have one bound is a negative of the other, see if the interior is an even or odd function. It's going to help you a lot. So how do you prove? You need to convince me now that this is an odd function. What is the definition of an odd function? This is true. How do you know it's an odd function? Yeah, good. F of negative x is equal to negative f of x. Evaluate the left-hand side, evaluate the right-hand side, check that they're equal. That's it. Notice x to the 4 is an even function. Cos squared is an even function. Sine is an odd function. Even times odd is odd. So is it the case that every time we get even times an odd function? Yes. Yes. Yep. But just be careful. If you have an odd times an odd, you'll get an even. So just be careful of the combinations. It's always very useful to check this condition for yourself. Check it using algebra. This will never steer you wrong. So if you have like extra time on your test, do you guys want me to, verify that this is odd, or do you think you guys got it? Like, I don't need to show this because it's just algebra. Okay, cool. Every convergent series has a unique sum. Is this true or false? Okay, so Subhanu thinks it's false. Anyone else? Okay, Harel thinks it's false. Who else? You think false? Oh my God, I'm so sorry, guys. There was a bunch of people in the waiting room. Zoom, for some reason, didn't let me get rid of the waiting room feature. Sorry. This one's false. False. Okay, everyone thinks it's false. Why? If you're right, it's false. But why? But these are only for convergent series. That's an example of a divergent series. Okay, but Harel, the sequence going to zero doesn't mean that the sum equals to zero. So the sequence is different from the sum. Be careful of your definitions. It is false. Okay, but that's an example of a convergent series that has a unique sum. But we're saying that every convergent series has a unique sum. Nick got it, basically. Do you guys remember learning about convergent, like conditionally convergent series? Conditional convergence. Convergence has two different categories, conditional and absolute. Consider any conditionally convergent series. Conditionally convergent just means that you can rearrange the sum in any order you like, and you can get a different sum. It's really cool, this like concept. But essentially, that's what conditional convergence means. It means that you can get a different sum anytime you rearrange it. You can rearrange elements of the sum to get a new total. Absolute convergence just means that you have a unique sum, aka you can't rearrange the elements to get a new number. Does that make sense? So is this true? Every convergent series has a unique sum? It's false because of the different types of convergence. No, not each term has a unique sum. So when I say sum, I mean this, let's just say, going from this to of like an, this could equal to 2. If it's conditionally, you can't use a counterexample here. This one, you can just say that there's two different types of convergence. It would be really hard to find a counterexample for this one. But you would just say there's two different types of convergence, conditional and absolute convergence. Conditional convergence means you could rearrange the elements of the sum and get a different number. So for example, let's just say we have a generic series. This ordering of this series could give me 2. But if I just rearrange the elements, say I add A1 first, and then I add A 20 million, and then I add A10, and then I add A50, and I keep going, I could get a different sum. I could get that it equals to 3 instead, just based on the order that you're adding things. That's what conditional convergence means. You can rearrange the elements to get a different sum. When I say sum, we're going to go back to like, yeah, oscillating functions, basically any function that you could use AST on. So like your -1 to the n, right? Yeah, but that's divergent, right? So keep in mind, like -1 to the n is divergent, but you could do that for other AST-esque series. Okay? Does this concept kind of make sense? Really important to know the types of convergence. Okay? I'm moving on. This one. How would the integral look like for part E? This one? Oh, if the integral was, okay, if it was even, then it would look like this. If your function was even, it would just be 2 times the area of just one part, one half of it. Okay, this question, true or false? Sorry, I think I wrote 5 instead of 6. What do you guys think? Is this true? Good catch. It diverges. I like to put these kinds of trick questions in here just to make sure that you guys aren't jumping before checking for yourself. The geometric series, but check if your ratio tells you that it converges or diverges. This can only equal to a number if it converges. Your ratio in this case, what is it? It's pi over 2. Yeah, your ratio is pi over 2. What do we need to check to guarantee that it is? Well, we have to take the absolute value first. The absolute value is greater than 1, which means that this diverges. Exactly. So be careful of checking the conditions before jumping to conclusions, okay? So this one is false. Can't find the sum if it diverges. Okay, lovely. What about this one? Assume all functions in this question are continuous on R, okay? Let A, B be in R, so they're real numbers, and A is less than B. This is just to make sure that our bounds are well defined. Then the consequent of the FTOC corollary is equivalent to this. Remember what the FTOC corollary tells you. It says that if your interior function is continuous, then it is integrable. And if you can find an antiderivative of it, all you need to do is take f of b minus f of a. Exactly. By definition, h prime is an antiderivative of h double prime. Exactly. You remove one tick mark, one derivative, and it becomes the FTC corollary. This is just to trick you guys, to make sure that you guys understand what the FTC corollary actually means. Okay, this is an antiderivative. Or, yeah, antiderivative. Oh, wait, whoops. Whoops, no, this guy is the antiderivative. Okay, cool. I thought you guys were gonna get tripped up on that question. I'm glad to see that you guys didn't. Okay, every function has more than one antiderivative. Okay, people saying true, 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 I guess. Oh, everyone's saying true, but what if I said this? Yeah, it's true if it's continuous. Be careful of checking the conditions of your theory. You can only find an antiderivative if it's integrable. It may not exist. Yeah, be careful of that. This is a question that I would have gotten wrong a couple of years ago. So if your function is integrable, then it will have more than one antiderivative that would differ by, yeah. So this one's false. Be careful. Be careful of conditions. Yeah. So so requires. So what condition would wait, no. This is a false statement. Every function has more than one antiderivative is false until you add the condition of being continuous. So I put the addition of if it's continuous. Requires in yeah, it wasn't part of the original statement. So that's why I erased it and put a different thing in. Okay. We good with this one? I'm a really big fan of questions like this where it's just one piece of information is omitted and that changes everything. All right. What about this question? Again, this is like a tidbit from the first half of the course. Yeah. This one? Okay. Merrill thinks it's false. Anyone else? False. Okay. Anyone else? Vacuously true? No. You don't need to specify continuity here because like this could be just for any function, right? Even if the function were continuous. Like, yeah. F doesn't need to be integrable for this. Okay, why is this false? This is false. Why? Darboux definition. Yeah. Do you guys remember what the Darboux definition of integrability is? It's integrable if and only if. For all epsilon greater than 0, there exists a partition of AB such that UF, or no, we can use epsilon reformulation. Don't even bother with Darboux because you don't have all the UFPs, right? Notice it says there exists some partition, right? So you're already given a partition. It's integrable if and only if this, right? But we have that the UFP minus LFP is equal to, would that be a +3? There exists some epsilon that is less than 3. But that would make it for all. Couldn't it be true for a different partition? But this is like satisfying, like if it was a, man, now I'm like, these existential quantifier questions are like really tricky. There exists a partition for all. Right, but let's just say, so the key lies in the phrasing of the question. It must be integrable. Just because we have this example of a partition doesn't mean that it is integrable, right? It could not be integrable. Yeah, it says it must. This is not sufficient to say that it is integrable, right? Just because we have a partition that leaves you with like a choice of epsilon, right, for that partition, right? Yeah, it doesn't mean that it's integrable. Yeah, consider the function that Nick said, -6, -9 for in Q, not in Q. Like this is a function that we know is not integrable that has this property, right? Exactly. It's not integrable, but it satisfies the condition that's in the setup. Does that make sense? Just because it has there existing a partition part doesn't necessarily mean that, yeah, it may or may not be. It's not sufficient to say that it is going to be integrable. Yeah, the key lies in the phrasing. So be careful. The thing must be integrable. False. Cool. All right. Suppose that G is at least twice differentiable on R. Okay. So what that means is this exists and this exists. Okay. If G of 0 is equal to 1, then G of 4 is equal to whatever that is. Do we think this is true or false? Okay. Benedict thinks it's true. Who else thinks it's true? Or is there someone who thinks it's false? True. Okay. Everyone thinks it's true. Hey, you guys got it. It is true. Oh, there you go. It is true. The reason it's true is because consider just this guy. What's an antiderivative of this? G of x. Cool. And we can compute this because it's a definite integral. We can use FTOC on it. We can rewrite G of 4. So we get that this is equal to G of 4 minus 1 by the given. We know that G of 0 is equal to 1. Then move the -1 to the other side. And you get exactly what you need. This is true. Yeah, you move it to the other side. Here's a question for you. Why do we need twice differentiable? Why do we need that this exists? Yes, so that G prime is integrable. Yeah, we wouldn't be able to use FTOC on it if G prime of x wasn't continuous. We wouldn't be able to. has to be continuous to do this. Yeah, but I like to say twice differentiable because differentiability. No, yeah, we could say it's continuous, sure, but twice differentiable gives you continuity. Continuous first derivative? Yeah, but I didn't want to give that to you guys, right? That'd be like giving you the answer. Twice differentiable gets you to think outside the box in terms of what does differentiability give me in terms of tools. I don't want to give you, I don't want to hand over to you guys the answer. I want you guys to think a little bit. Okay. Are we good with this question? Pretty self-explanatory, pretty easy. I'm gonna move on. Okay, this is the last true and false question. Suppose this is a power series. So suppose this power series converges this at x equals 4 and diverges at, so this is convergent at x equals -6, it diverges. Then we have that this converges. The trick with this is we want to find what the interval of convergence is. Find the interval of convergence. AKA the x values. Where can my x values be such that my series converges? So I'm going to draw a little number line. This is 0. This is going to be where 4 is. This is where -6 is. So at this point, we have convergence. We don't know what kind of convergence, we just have convergence. At this point, we don't have convergence. So what can we say about the size or the length of our interval of convergence? Where does my interval of convergence live? Any ideas? It's just 1 point? Or is it an interval? Between -6 and 4? Not quite. All right. Notice that this is a power series centered at 0. Centered at 0. So that means that my middle of my series, yeah, is going to be 0. So right here is going to be the middle. What's my radius? What's the least possible radius of convergence or the most possible radius of convergence that we can claim? We can claim that R is equal to 4. Most. Right? If we have convergence at 4, we know that our radius of convergence, we can go 4. It has to be a symmetric interval. Yeah. It's symmetric. It's symmetric about the center. So it has to be up until -4. So we have that between -4 and 4. That is our most, we can actually include this, most interval, or the biggest interval possible. Biggest interval we can claim. Does that make sense to everyone? It has to be a symmetric interval. It revolves. Why did I not include 4? Because we're not told what happens at -4. We're only told what happens at 4, right? If I'm not given that it can happen at -4, we don't include it just by default. I don't know that information, so I'm gonna like it doesn't exist. But I know it converges to 4. If I plugged in 4, I could claim that it converges there. So I put the closed bracket around the 4. So what do you mean, Sabani? Okay. If we Sure, Harel. We're gonna take a break in about 5 minutes. Like, what if the question asks where it diverges? Well, you wouldn't be able to tell me where it diverges. You would just be able to tell me that at most we know it diverges everywhere else. That's not our interval of convergence. You just find the everywhere else. We wouldn't even be able to claim that it diverges. How do we know it doesn't converge at x is greater than 4? Because we know, like, this is the biggest interval we can claim. We can't say that we don't know, right? Like, we don't know it doesn't converge there, but we just know the biggest interval we can claim it converges at is 4, right? The biggest hour radius of convergence we know to be is 4. So we're just going to use that. We don't have enough information to say it doesn't converge when x is greater than 4. Like, r could be 5, and we don't know that. If it was centered at 3, would it be 2, 4? Yes. Yes. That would be if it was centered at 3. Okay, but now that we've analyzed the power series in general, let's analyze this guy, the power series with an x value plugged in. What is the x value that's plugged in here? What is that x value that we see plugged in? Do a little bit of algebra, blend together certain powers. What? Yeah, this is equal to -3. Is x in this interval? Is -3 in the interval? Yes. So we have convergence. So this is true. Is the max of the interval? Yes, exactly. The max of the interval of convergence is going to be at -6 to 6. Like, that's the biggest it could be. But we don't even know what's going to happen around 5 and anything in between 4 and 6. So we just omit that. Assume it doesn't even converge there. Does that make sense? How do you get x is equal to -3? Just a little bit of algebra. I'm going to choose to do it around here, okay? Sorry, this is not going to go. -1 to the n, Cn, 3 to the n. -1 to the n times 3 to the n, Cn. Merge these two to be -3 to the n, Cn. Does that make sense, Jimmy? Yeah. Cool. All right. That is all that I have for the true and false. Are there any questions, last minute questions, or questions of clarification that need to be done for the true and false? Anything that anyone was confused by? Anyone want to go back to like take, I don't know. How do you know it's centered at 0? Because a power series looks like this, Cn times x minus a to the n. Is there an a? What is a? Yeah, I know. This question is a really tricky one. Yeah, can you show us the question ahead? Sure, if you really want. It's just a definite integral by definition question. I'm debating whether I even go through this question. I think you guys seem to get it. Unless you really, it's been like so long, you really want me to do it. And notice I'm forcing a certain technique here. That's a terrible grain. I'm forcing a certain technique here. I want you guys to use a certain technique. The true false before. Okay, oh, way before. So like up here. I know some of you guys came in late, so okay, it would be a great help. Okay, how about not geometric? Riemann definition is not geometric. They're not the same thing. Riemann definition is, okay, we'll go over it. We'll go over it after break. So the center point for this, The center point for the second power series is 3. No, it's not the center point. The center point is still 0. The center is still 0. It doesn't change for a specific series. But the point that's plugged in, the x value that was plugged in is -3. If you plug in -3, it's going to converge. If you plug in 4, it's going to converge. If you plug in 0, it'll converge. Does that make sense? Yeah. Do we have true and false? I would assume maybe like a true and false-esque question, but it's still really important to know these things. I would assume it would be like a short answer of sorts. All right. Are there any other questions from the true and false section before we take a break? Is everything kind of clear for the most part? Okay. Question. Was this question helpful? Very confusing. Okay, but helpful. So it's very confusing because you haven't. That's why I asked if you guys have studied before the review seminar. I'm not going to go over every single concept that you guys talked about in 837. That'd be ridiculous. I'm not going to teach you definitions. I'm not going to teach you theorems. Those are things I expect you guys to already know. But teaching you how to do certain questions using certain definitions, using theorems to solve certain types of questions. That's what I'm trying to teach you guys. So if you guys didn't study these things, so for example, the power series definition, it's important to know that this is just an application of the power series. Okay. Does that make sense? So this question is challenging because it's reliant on your definition knowledge. And if you guys don't know the definition, then well, it's a wash. You guess, and then maybe get part marks. Okay. But no other questions for the true and false? Okay. In that case, we'll take a 5 to 7 minute break. Okay, we'll be back at 2:15. Sound good? Unless you guys want to keep doing math. Okay, I'm guessing not. So don't worry about missing the first 20 to 30 minutes. I know a lot of you came in late. We'll be posting the recording. Yeah, I'm recording, and the recording will be posted. So don't worry about that. You scroll up first long question. You're welcome, Danush. If you guys have any questions, this would be the time to ask. Okay, power series, really quickly. Okay, like the concept from the start. Okay, a power series is a specific type of series that looks like this. It has X in it. Normally, that's not normal, right? We don't see X in our series. A power series is just a way of rewriting a function of X, okay? In terms of like a polynomial, okay? And you'll see this later on when you guys see Maclaurin series or Taylor series in your courses. But for now, this is all we need to know about power series. Power series have a smaller series in it, and they have what's called a center, and they have the X value. There are a few key features of a power series. A power series goes hand in hand with a radius of convergence, r. So this defines our radius of convergence. And then an interval of convergence. These two are different things. The radius of convergence is just a number. An interval of convergence, hence the name, is an interval. AKA, it'll be something like this: a minus r, where a is the center, and a plus r. Notice these brackets, they can be closed brackets or open brackets, depending on the behavior of the series at a certain point. Your x values are going to be in this interval, okay? For your series to converge at a certain x value, if you were to plug in a certain x value, your series would converge if and only if the x value is in the interval of convergence. Okay? If you plugged in any other x value, you would have divergence. Okay? Notice this interval is also symmetric about the a value. Notice a radius is always symmetric, right? It creates like a symmetry of sorts. In the other question, we had a being 0. A, the center, was 0. So we only had to look at the radius of convergence, basically the smallest value that guaranteed convergence at a certain point. Okay. We just need a way to claim that between -4 and 4, we had convergence. Okay. That's pretty much it when it comes to power series. That's kind of all you need to know. All right. But there's an approach, there's a certain understanding that comes with power series. You guys need to know this. All right. Because I guarantee you a question that will come up on the final exam. Will I be posting this? I won't be posting the worksheet because these are like my curated questions and I don't want them to be out there. But I will be posting this video, the video recording. Our graphing questions, like, no, we typically don't ask you to graph things. We expect you to know the graphs of certain functions, but we don't ask you to graph things. That's more of like an elementary, like high school kind of concept that, no. At least I wouldn't expect it. Okay, our power series is a little bit more clear to people. We'll go over the way to find R, like the radius of convergence, later in the review seminar. Okay. All right. Okay. Any other questions? Yes? No? Okay, no questions? Okay. Okay. Is everyone kind of back for the most part? All right. You can put thumbs up in the chat if you're back. If you're not back, Maybe we'll give people like 2 minutes or something. All right. Are you guys feeling energized, ready for some more math? Okay, cool. So, long answer question. We've already gone through an hour. Do we still want to do this question? Do we feel like it's necessary? Or do you want me to just walk you through it kind of just a little bit? Yes? Okay. We'll go through it really quickly. I'm going to need full attention from all of you, okay? We'll go through it. So, by Riemann definition, we have that this is equal to the limit as n goes to infinity of I equals 1, okay, yeah, 1 to n, sorry, 0 to n, because we're starting with a right Riemann sum, of f of xi star dx, or d theta, sorry, delta x. Cool? So we know what our function is, right? F of x is equal to fx 5x squared minus 2x plus 1. What's our delta x here? We have a few components that we need. Delta x is equal to b minus a over n, where b is 1, a is 0, 1 minus 0, and then we have 1 over n. Cool. All right, we also need to know what xi we're choosing. I would suggest always going for a right Riemann sum, hence we're going to choose xi, not xi minus 1, not a midpoint sum. We're just going to choose xi, keep it simple. All right, xi is defined by a plus I delta x. We know that a is 0 plus I, delta x is 1 over n, so I'm just going to write it as I over n. All right, cool. So now just plug in chug, plug all these things in. I equals 0 of, well, our function is 5. Sorry, I'm going to write it on another line because I'm going to run out of space. The limit as n goes to infinity of I equals 0 to n of 5 xi squared minus 2 xi plus 1, and then times delta x, our I over n. Keep expanding, keep subbing things in, and then just whittle it down to a number. These are where you're going to need to know your common sums. It's going to be I over n squared minus 2 I over n plus 1 I over n. The limit as n goes to infinity. I equals 0. 5i squared over n squared minus 2i over n plus, actually, let's do cubed just to put it all together. And then plus I over n. I just distributed the I over n in. Okay. Now just remove elements. Well, not remove elements, but just factor things out and split the sum accordingly. So 5 over n cubed can be removed. I equals 0 to n of I cubed minus 2 over n squared. I equals 0 to infinity, or sorry, 0 to n of I squared, and then plus the sum of just I with 1 over n removed. Delta x be, oh, yes, you're right, sorry. I was wondering why I was getting weird things. So this is going to be a 1. There we go. Cool, we're good now. Good catch on that. All right. Now, we just need to use our common sums. Remember your common sums for things like I squared, just 1. These should be like kind of ingrained in you by this at this point. So 5 over n cubed, n plus 1, n 2n plus 1, all over 6, minus 2 over n squared of n times n plus 1 all over 2, then plus 1 over n times n. Lovely. I like that you remembered that, Anthony. Okay, we good? I didn't make any mistakes? Now, just calculate the limit. Cancel things. Yeah. Yeah, he would. Calculate your limit. That's it. Cancel things where you can. This n, they cancel to 1. These two n's will cancel with these two n's. This is going to be a 1 over n. Okay. And then the 3 n's are going to cancel out as well. What you're going to end up getting is something like this. So if you guys show all the math, you're going to get 5 over 3 plus 1 minus 1. Or order matters, I guess. 1 minus 1 plus 1, which is equals to 5 over 3. This kind of question is free marks. I will have you know that. You're just showing a left-hand side equals right-hand side. And just make sure you do a specific technique to get there. How is this? Does this feel familiar? Feel easy? Just tedious. Yeah, but once you get the process down, it's free marks. You know it, right? Like, heck, it's been like 4 years since I've done this last, kind of. And I still just know it. It's tedious, sure, but free marks. Okay, we're good with this. You can give me a thumbs up in the chat if you feel comfortable with it. If you don't, you can message me privately or something. All right. Cool. What about this? You guys feel comfortable with disproving integrability? There are so many questions like this. Do we even need to do this? Okay, Anthony says no. Nah, Anjali says okay. Okay, I'm just gonna go over the 3 techniques to disproving integrability. Exactly. Just show what they're gonna equal to. Like just show what the 3 techniques are. Okay, so there are 3 techniques to disprove integrability. The 3 techniques are the Riemann definition, right? By choosing a partition. There is Darboux, which you just do the inf of the lower sums, or inf of the upper sum, sorry. Is equal to the supremum of the lower sums. And then if you show that they're not equal, then you're good. And then there's epsilon reformulation, my favorite one. It's very straightforward, very formulaic, gets you really just, it's super easy to not even memorize. You don't even need to memorize it. I just understand it and kind of get there. But these are 3 techniques. If you know how to do each of these, you're good. I would actually say do this question, try it all 3 different ways, just as practice. Okay? Okay, I'm gonna move on from this one. What would be a good partition to choose? It would be, you would have to choose an irrational plus some choice of a rational number. Some number that you know is in the interval, and then choose your I, the thing that you're defining your partition using, is like some rational number, like 1 over root 2 times I. Yes, you have to choose a specific tag partition. Yes. This is super challenging. Hold on. This one is super challenging. This one is eh. This one is the best one. That's my ranking for these ones. Yes, that was on the midterm. There was a choose a partition, choose a specific one. Yes, exactly. Epsilon reformulation is the UFP minus LFP is going to be less than epsilon, but you just show that it's greater than epsilon for some choice of epsilon. He might not put it on the final. It's the easiest, exactly. Yeah. If you need more practice, there's a bunch of questions on the quizzes that use the Riemann definition. There's some that use the epsilon reformulation question, like types of thing. So just review those, okay? And try to understand them to the best of your ability. Okay, we're gonna move on to finally the good stuff, the stuff that people need the most practice with, from what I've seen. Okay. This is where it's gonna get a bit messy, okay? I'm gonna go through each of the techniques and what signs there are to use them. So we're gonna create our integration technique checklist. Integration checklist. Okay, do you guys remember all of your techniques? Okay, start listing off some techniques in the chat. U sub, my favorite. Trig sub. PFD, nice. Parts, yeah, integration by parts. Geometric, good. Inspection, sure. Anything else? Any other techniques that we're missing? Yeah, I don't think so. Okay, so here is my checklist. My checklist is always geometric first. So geometric is always the first thing you want to check. Can I integrate this geometrically? As in, do I have bounds for me to be able to find the exact signed area in that interval? Number two, what would you guys place as number two? Inspection is not really a technique. It's more so just like, okay, can I just find the antiderivative? I would say U sub. Okay, what would you put next? U sub's off the table now. By parts, yeah, exactly. Then PFD, and then what should we always do last? Yeah, trig sub should always be done last. Trig sub is long, trig sub is tedious, trig sub is not like the others. It's annoying. Hence, choose it last. There's only one specific case where you would ever have to actually do trig sub, and we're gonna go over that later. Okay. For geometric, the reason you always check it first, you check this first when you have bounds. Bounds on a simple looking function, aka a square root function in particular. When you have a square root function, always check if you can just do it geometrically. Okay. Actually, I'm gonna add one more thing in here. I'm gonna add, always keep in mind your properties. So properties. So like even, odd, things like that. PFT is 5 and trig sub is 6. A U sub. U sub, you use it when you see a derivative of some function that's already in your integrand. So you have your integrand, and in your integrand, you see some function and you find its derivative multiplied to it. It's essentially what your reverse chain rule is. When a derivative is in integrand. Okay, your by parts is usually when you have a product of two functions that don't seem to relate. Your PFD, obviously, when you have a rational function. And then your trig sub is going to be your very last resort. Okay. All right. Basically, Nick kind of gave us the answer. This is going to be a by parts because we have two functions multiplied to each other that don't seem to relate at all. But now you just need to make sure that you choose your u and v appropriately. So u, what would you choose u to be? Keep it simple, 2 to the x. All right, what's dv going to be? Cos x. Cool. Cos x dx. All right, so now just differentiate your u, integrate your v. So this is going to be a negative, or not negative, just v is going to be sine x. And your du is going to be, yes, yep. Yeah, it's really hard to find the antiderivative of 2 to the x. So whenever you have like an exponential function, you always want to take the derivative of that. Yes, good. Don't forget your derivatives of these common functions. All right. So now, how do we plug this in? The formula is uv minus v du. So let's plug it in. U is 2 to the x. V is sine x minus the integral of v. V in this case is sine x. And then we have ln 2 times 2 to the x dx. Cool. Keep it going. This is gonna, notice how these are gonna loop. If you factor out the ln 2, you'll still get a sine function and a 2 to the power of x back. Do integration by parts again. This is what we like to call a circular or a recursive integration by parts. And basically what you do is you choose the exact same choices of u and dv. So if you chose u to be your exponential function, choose u to be your exponential function again. But be careful because we already used u, so let's give these guys different names. u1 and v1, I should say, because we're going to do it again. Keep your math clear. Right? So now u2 is going to be 2 to the x. dv2 is going to be sine x dx. du2 is going to be equal to 2x ln of 2 dx. And then v2 is equal to negative. Does that make sense? When you're naming your integration by parts like variables, give them unique names. It could be u1, u2, v1, v2. All right, because you can't be reusing variable names. So u1, v1 minus, here we go. Then just do it again. So we still have this part. And then it's going to be minus uv minus, again, v, so negative cos x, and then du, so 2x ln 2. I'm missing a ln in here. Does that make sense? Thumbs up if we're good with this so far. This is just me cleaning up a little bit. Notice what we have here again. Isn't the last term negative? Yes, sorry. Yep, when you distribute the thing, yeah. The OG function, give him a name. Call it I if you want. Call it Jerry, because Jerry's another goat TA. Right. So now let's isolate for Jerry. Jerry is equal to all of this, right? But moving the Jerry to the negative ln squared to Jerry. Well, okay. Moving it to the other side, we get plus ln squared to Jerry is equal to, and then all the rest of it. Sine x ln plus ln 2x cos x, and then factor Jerry out. What's going to be remaining? Okay. And then just for this step is where I would add the plus c. So 2x sine x plus ln 2x cos over 1 plus ln 2 squared is equal to Jerry. And then plus c space, but are we good with this? It's just a little bit of added algebra to an integration by parts. Are we good with the renaming in terms of like U2 and U1 and stuff like that? Like giving them unique names? Cool. So I can move on? I'm going to assume it's a yes. All right, next question. What do we think this kind of question begs for? What do we see? Okay, this looks like U sub. Okay, what's going to be our choice of U? Root x. Okay, I like it. So U is equal to root x. All right, what's du going to be in that case? Cool. Can we rewrite this part as U? Can we replace the root x with U? Like if we want to bring the U to the other side, like so if I want to do something like this, I can't mix variables, but I know what that equals to in terms of U. So I could just replace it, right? So 1/2 dx. Or you could do 2u, it really doesn't matter. Cool. So now I'm just going to plug that stuff in. So e to the u is still here. How can I make a 1/2 appear? So I have the dx part. I need a 1/2 as well. How can I make that appear? What can I always do? Move it to the other side. Sure, you can do that too. Sure. Okay. We'll do it that way. All right. Now what? What does it seem like? Differentiate? Yeah, it's by parts. These are two functions that don't seem to have any relation to each other, right? Integrate, nice. So now we're moving on to an integration by parts. So you can always combine more than one integration technique to be able to move forward. So in this case, we can't use u anymore. Why can't we use u? Yeah, we already used it. Give it a different name. Sure. Nah, I don't like u prime. Sure, let's call it w. Because we're going to use v anyway. So w is equal to, you know what? Let's name it Poria. Why not? Make it fun. Poria is equal to 2u, the thing that you want to differentiate. For. All right, then our dv is going to be equal to e to the u du. What's Poria prime going to equal to? Or d Poria? 2 du. And then what's the antiderivative of e to the x? Or e to the u in this case? Good job. E to the u. So now, plug it in. It's going to equal to uv, or in this case, Poria v, 2u times e to the u minus the integral of v du times 2 du. Cool? Now what? Do we need this integral here anymore? The integration sign? What does the second half become? 2 e to the u, because the antiderivative of e to the u is just e to the u. We need a plus c, like Anthony's mentioning. Is that it? Is that our final answer? Not plug in u and v, but we need to take it back to the world of x. Yes, our original integrand, our original integral was in terms of x. You need to always take it back to the original variable of integration. So we have a definition for u. What was u again? What did we say u was? Square root x. So wherever I see u, I'm going to replace it with square root of x. Bam, done. How do we feel about using multiple different techniques for one integral and identifying it? Cool. Not too bad. We're picking it up. We're picking the pace up a bit. Let's do a more challenging question. What do we think? What are the signs here? So my little tip to you guys is always simplify your integrand first. My tutorial knows this very, very, very well. Always simplify your, yeah, exactly. Sine squared can equal to, actually, I'm gonna do one thing first. Too well. This is a definite integral. I'm gonna completely disregard the fact that it's a definite integral for now. This looks like a really complicated integral. I'm going to consider the indefinite integral first. Consider indefinite integral first. So now I can do my substitutions and stuff. 3 cos x plus 3 minus. We said that this became 1 minus cos squared. This is just by your Pythagorean identity. Turbo definition, absolutely not. So What does it simplify to? What does that denominator simplify to? Cool. Yeah, it's a -1. All right. Now what? What do we notice about the denominator? What does it look like almost? It almost looks like it almost looks like a polynomial, a quadratic in this case. Is there anything that we can do to make it look more like a polynomial? Maybe change the variable or something. U sub. What would we want to take as our U? U is equal to cos x. Perfect. Why did we choose U is equal to cos x? Yes, the sine x gets turned into a du. Lovely. Minus sine x dx. So I'm going to move the -1 to the other side. So that's okay. So now it's going to be -1 in the numerator, 2u squared plus 3u minus 1. Oh, would you look at that? We have a polynomial. Did you get a -1? Moving the negative to the other side. The derivative of cos is negative sine. Oh, it's supposed to be +1. Yeah, sorry, you're right. Oh, I forgot to put the thing in du. Yeah. Yeah, now it's a partial fraction decomposition. This is something that you should be able to easily factor, right? For partial fraction decomposition, we need to verify first, is this a rational function? Can we guarantee that this is rational? Because we can only do PFD on rational functions. Does this ring a bell? A rational function, you have to guarantee that the degree of the numerator is less than the degree of the denominator. Otherwise, you can't do PFD on it. So maybe the tricky thing is he may give you an integral where the degree of the numerator is greater than the degree of the denominator. What could you do in that case? If we had the degree of the numerator is greater than or equal, yes, you do long division, and then you'd be able to do a PFD on the smaller part by using the remainder theorem. Long division, and then find a way to rewrite the numerator. Do you guys remember this? You have a polynomial. So call it P of X. Okay. Divide it by some divisor, right? Some polynomial where the denominator is smaller. Okay. So the divisor, thing you're dividing it by. When you do polynomial long division, so you do P of X divided by the denominator, gives you a quotient that is a function of X. And then at the bottom, you get a remainder, some other function of X. This is, yeah, maybe, but I don't know. He might give you a question like this. So I just want to make sure you guys know how to do it. When you are rewriting your polynomial P of X, what you can do is rewrite it as you can take the quotient and the divisor, multiply them, and then add your remainder. That's going to give you your original function. This is really useful because if you're dividing by your divisor, if your polynomial right here is divided by your divisor, we get a nice simplification, right? Specifically in these. And then you can integrate. But this is like a specific, very specific case for when your degree of the numerator is bigger than or equal to degree of the denominator. You can always do this, okay? All right, but for this part, you would just factor. It would be 2u plus 1, and then u plus 1. Yep. And then you would just integration by parts. Or not, sorry, PFD. You would PFD this. Okay, I'm not going to go over the PFD, but your final answer should look something like this. Actually, I'm not even going to write the final answer. You guys can figure that out. I don't have it written down. I didn't bother writing it down. Okay. We good with this? I really like questions like this where you have to do algebra first. Sub things in to make it look nicer. Okay, move on. What about this question? What does this kind of look like? Geometric, okay. Could you draw this function? Is this drawable? Anthony can't. Circle with radius square root 6? Not sure about that one. I don't think you can draw this one. Hi, I can't draw it. Desmos it. Unless you get a Desmos on a final exam, I don't know. So this one is a rare case where you can't draw it. Okay. Specifically, we thought of geometric because we had the bounds. The bounds were nice. It was a square root function, which was also really nice. But the format of the square root function was not it. This is one of the rare cases where you want to do trig sub. Okay. Very, very rare. The first thing you do is complete the square. Annoying. Bad question. Terrible. But your choices of u are going to be a sine theta, where it's equal to x minus 3. Okay. Your theta is going to live between negative pi over 2 to pi over 2, inclusive. If you guys can complete the square, do this question. It's so easy. You just need to be able to identify what's the choice of u. What's your a? In this case, your a is going to be root 6. Or no, sorry. Yeah, it is root 6. Wait, no, it won't be. It'll be something. Whatever the number is after you complete the square. I didn't bother completing the square. I was going to do it for you guys, but then I was like, we're running out of time. Okay, do you guys remember how to complete the square? Do you guys want to recap a lesson on it? You guys actually, yeah? Oh my God. Grade 10. This is grade 10. Okay. So completing the square. Your goal is to get from this to something like this. Okay. We're gonna put this in chronological order in terms of like the, natural ordering of polynomials. Okay. Highest power first. Factor out anything you can. Your first step is factor out anything you can from the first 2 terms. In this case, we only have 2 terms. Not wrong to do a quick U7. See, you could, but you would have to make a du appear. You couldn't always do that. It's not multiplied by this. That would make it needlessly complicated. Yeah. So complete the square. So the only thing I can factor out from the x squared is a -1. So the coefficient of x squared is the thing that you want to factor out from the first two terms. There's only two terms here, so I'm just going to factor that out. Then you want a perfect square trinomial to appear. The way I can make that happen is adding a convenient choice of 0, so plus 0. The choice of 0 is going to always be plus or minus the b term, so the middle term, this guy, over 2, all squared. Okay. So in this case, b is 6. So it's going to be 6 over 2, all squared, which is going to be 9. So it's going to be plus and minus 9. You want to put the positive version on the inside, the negative version on the outside. Right? Make sure you're, whenever you have like something that's factored out, you always make sure you want to have the brackets around the positive and negatives. Okay. Then this becomes a perfect square trinomial. Cool. Factor it. And then distribute the negative. Does that make sense? Give me a thumbs up or a smiley face or something in the chat to indicate that you got this. Okay. This is not a hard thing. Okay, cool. Lovely. You guys understand the adding 0 step. Okay, cool. That's something that they typically don't teach you in high school, but I want to make sure that you guys know it. Like, as in, like, you could kind of just make this happen. Okay. This is just always a trick that you do. Then, do you see how your choice, you're going to have something like this, right? 9 minus x minus 3 squared. Your choice of a is going to be 3. Your u is going to be x minus 3. Okay. Because we have something of the form a squared minus u squared. Then do a trig sub. It's actually super simple, this one. Okay. And just make sure that when you're doing your trig sub, you always take it back to the world of x. Don't forget to take it back to the world of x. You can't leave your final answer in terms of theta. Okay, if we have time near the end, we can go through this question more, but I do want to get through other questions. Unless you guys want to be here all day, and then I can just do math all day. I'm cool with that too. Yes, with any question that starts off as a definite integral, you can always say, I'm going to consider the indefinite version first, and then just find the antiderivative, and then use FTOC corollary on it. You can always do that, okay? Yeah. All right, do I need to go through this question in depth? No, okay. No, okay. Lovely. Because I don't want to have to. I hate doing trig sub as much as you guys do. Right, next question. So you have to make your choices of A and U, and then sub them in. You have to differentiate your U. So du is going to be equal to something. A cos theta d theta. And then you just sub things in. Okay. For this one, factor out of square root x. You do that. I like that idea. You can simplify this a bit. These two you can cancel kind of. Then it's arctan square root x. For the previous question or this one? E, this one. I don't know about that one. Well, does this, okay, we have bounds. Can you graph this function? Does it seem geometric? Could you do a geometric kind of thing? No. Cool. So then that means we're going to do a U sub. What could your choice of U be? Square root x? Yeah, I like that. Root x, that's kind of the problem child, right? So I'm going to choose U to be root x. U equals root x. What's my du? It was before. Yep. Well, can we say that this is the same thing as root x squared? We can do that, right? Yes. So we have 2 du is equal to 1 over root x dx. Notice we have a 1 over x dx here. So I'm just going to sub that in. Then this also means that x is equal to u squared, right? This is going to be a u squared. And we have a u squared plus 1 du. Well, now what? Is this actually correct? Did I do something correct here? Yes, the bounds. Good. What do the bounds need to change to? Yes. Whatever you chose to be u, plug in your bounds and then replace them. So u is 1, or u is root x. What happened to the 2? Oh, sorry. Okay, so it's going to be root 3. It's going to be root 1, which is just 1. Wouldn't it be u cubed at the bottom? No, would not be. In the denominator, we have a 1 over root x. Yeah. Let me just make sure. Yeah, now you would do it by parts kind of thing. You would be able to integrate this part, which would be just arctan, and you would differentiate the 2u squared. Okay. I'm just going to write that part down. So 2u squared multiplied by 1 over 1 plus u squared. Yeah, you can find the antiderivative in terms of x first. But the reason I chose to do this is because I already showed you guys that you can consider the indefinite first, find it in terms of x, then plug things in later. But I wanted to give you guys another option just in case. The reason that I like to always consider the the indefinite integral first is because I hate dealing with the bounds. So I just ignore it until the very end. But you have to turn things into x first. Don't plug them into u. Okay? All right. So after this, you guys know what your choices of u and dv are? Well, u and dv. Thing that you're trying to differentiate is this guy. Thing that you integrate this guy. This is going to be arctan of u. This is going to be for u when you differentiate it. And then from here, it's pretty straightforward. I'm going to move on. Okay, what about this question? You can ignore what arctan of root 3 is. You don't need to evaluate what arctan of root 3 is. You could find it. Yeah. This is also a U sub. Why do you think it's by parts? Could you integrate or differentiate this? They look weird together. Yeah, you're right. Maybe we're getting ahead of ourselves. They do look weird together. Let's do a U sub first. I think it would look cleaner if we chose U to be some nice thing first. Let's do a U sub where U is equal to x, e to the x. Then we get du is equal to e to the x dx. What would you look at that? These go away really nicely. So we have arctan of u is something that we're trying to integrate now. Okay, I'm not going to go through this question fully, but we're not asking you to memorize the antiderivative of arctan. We're not going to have you do that. You should never do that. Whenever you're given an arc sine, arc cos, arc tan, and you want to integrate it, take u, like your u part. So let's just say like w. Take that to be the thing that you want to differentiate. We know what the derivative of arctan is, right? So I'm going to take that to be my choice of u. Okay. So that means that dw is equal to 1 over 1 plus u squared du. My dv, take that to just be du, aka 1 times du. You could integrate this, right? This is something you can integrate. This is just going to be u. Now do your integration by parts with this. How many of you guys knew that this is a technique you could use? Not at all. Okay. Not you. Okay. So this is a really cool technique that you can do. This was a question that was on my A37 final. And I didn't know how to do it. Isn't like this like the integral of inverse functions? Uh, kind of. Kind of, yeah. Essentially. But you guys don't need to memorize that formula. Don't memorize. Why bother memorizing when you could just understand it, know it, see what the technique is, be able to replicate it, right? Then you would just do your integration by parts like normal. Okay. Hi, Ali. I saw you come in. Okay. Bye, Ali. Alrighty. We ready to move on? Can we continue? Move on to this? You should always try a bunch of U subs first. Okay, that's just my take. Try a bunch of U subs. U sub is like literally the go-to technique. Okay. You good with this? Give me a thumbs up or a smiley face if I can move on. Cool. This question. Complicated beast question. What do we do? What do you guys think? A trig sub. Oh, no. Don't do tricks up on this. Take a look at the bounds. What do we notice about that? Yeah, there's a parity thing going on. Look at the bounds. Check if it's even and odd. Yeah, x times root or x times absolute value of x is an odd function because x is an odd function. Absolute value of x is an even function. Even times odd, even. Or sorry, odd. It's gonna be odd. What about the other side? You can break it up, sure. The other side's also gonna be odd. Notice sign is odd. The denominator is even. Even times odd is odd. The entire thing is an odd function. Sign is odd. If you drew it, odd. Cos is even, sign is odd. Yes. So the entire thing equals to 0 by odd function. You can also just by definition prove that it's odd. If it ain't broke, don't fix it. Prove that this is equal to this. No trig sub. Don't do trig sub. The only type of question where you're forced to do trig sub is one of those square root functions, like square root functions of like a weird thing. Don't do trig sub anywhere else. Or if it's a 1 over a square root function like that. Don't do trig sub anywhere else. Okay? This also showed up on my final exam. Guess who didn't know how to do it? Sorry. So in the final, if we only use a geometric, I would say more is always better. If you can prove something by definition, aka just do algebra, do that. I don't think that you guys learn the rules technically of odd times even, even times odd, but it could just be useful for intuition's sake. So we can try this with, yeah, exactly. If you see a negative a to a a, some negative value to a positive value, always check for even odd. That's why you always check if you have a definite integral first. If you have a definite integral, do geometric. If that doesn't work, check even odd. Okay? I just want you guys to be prepared for anything that's possible. All right, I'm gonna move on. This is a challenge question. This one is really, really annoying just looking at it, but it's really simple actually. I put a hint. We're not gonna do it in full. I just put a hint to kind of get your guys' minds going in terms of like what algebraic manipulations you can do, what you have access to, what you're able to do. For this, it would be a yes, multiply by the conjugate. And you're gonna notice that things simplify super, super, super nicely. This is a really nice integral. You just gotta make it look nice first. All right. Okay, what about the next one? H. Yeah, trig sub. Yeah, trig sub, guys. Geometric. Remember, bounds. You have a bound. It's a semicircle. Well, it's gonna be a half semicircle. This is a function semicircle where the radius is 3, but the area that we're integrating over is only this. That's all it is. Find area. Cool. Are you guys starting to pick up and see what, like, kind of understand the signs, the telltale, indicators of which integration technique to use? Just go through a mental checklist. Just a mental checklist. Okay, this question. This is I believe that is the answer, yeah. I believe so. What about the 3 interval? What do you mean? No. Oh, 1/4 times pi of 9, yes. 1/4. I don't know why I wrote pi like that. It'd be this. Yeah, it'd be this. For this kind of question, we're asking you to evaluate it, aka determine if it is convergent or divergent. This kind of question will show up on your final exam. What are the tools that you have when it comes to convergent and divergent? Or like, sure, you could take the limit. This by definition is the limit. CT, comparison test. That is the thing that you primarily want to use. Okay. Comparison test is only available when you have an improper integral. Improper. This is actually improper in 2 ways. There's a vertical asymptote at 4. It's in between the interval. Four is in between 0 and infinity, right? So there's 2 parts to this that are going to be improper. Be able to identify, hey, when there's an asymptote between the interval of integration. Okay. Yes, it's also improper at 0 and 0. You're going to have to do multiple different things here. Okay. I can almost guarantee that there may be a yes and 0 when you factor out the x in the denominator. That means that's a root of the denominator. Roots of your denominator are your asymptotes. Yes. So what would be the approach here? I can almost guarantee that Fourier will give you a question like this, where there is an asymptote, but yeah, it's in between the interval. You would have to split the integral between all of the asymptotes and all of the improper parts. Then no PFD, do a comparison test on each of them. If one, okay, and then you know your rules of convergent integral plus convergent equals convergent. Convergent plus divergent equals divergent. Divergent plus divergent, you need to compute it in full. Compute fully. If you get a positive infinity minus infinity, you can't tell. There's 3 cases here. Infinity minus infinity. No, divergent minus divergent does not equal to 0, because you'll have an infinity minus infinity. Oh, you were tricking me. Okay, yeah. Infinity plus infinity is divergent. Infinity or negative infinity plus negative infinity, that's also divergent. This is the only case where it's like inconclusive. You need to do more work. I would suggest for things like this, you would have to use CT. Does that make sense? So you would split up your integral using integral properties, and then determine where each of those integrals on their own would converge, diverge, and then you would look at the combinations of things. This question is really tricky. I would highly recommend you take the time to go through this. I'm going to tell you right now that this diverges, but I want you to figure out which one of the 3 cases it is. Show all your steps and put in the effort to do that. Okay. We are finally done the integration portion. How do you guys feel about integration? if the integral converges, don't find the value it converges to unless it tells you to. Better than you feel about series. Well, hopefully it'll feel better afterwards. We're gonna get to series soon. Evaluating series is literally the next section. We're gonna do a series checklist as well. And we're gonna come up with yes, these are considered hard integrals. These are challenging integrals. All the questions I've curated for this review seminar are very challenging. I would say that none of them are easy. Again, I took A37 4 years ago. Some of these questions are verbatim from my final exam, like exactly from my final exam. And some of those questions, well, the questions I put on here at least, I wasn't able to solve during the final exam because I didn't study. But yes, exactly. Choose, when you're bounding your functions, choose simple functions like 1 over x. Things that you know converge or diverge. Okay? So when you're finding a function for comparison, okay? So let me actually write that down. When you're finding this one diverges, but when you're finding a function for comparison, you always is bound by simple, nice functions that you know converge, like the behavior of, okay? So CT, if it diverges, you're finding a smaller function. Find smaller. If it converges, you're finding a bigger function. This one I would say is the hardest question of them all. Of all of the integral questions, at least. Okay, do you guys want to take a 5-minute breather-ish? Get some water, maybe go to the bathroom, whatever. We may be here for another extra hour. I do apologize for that. But I really do want to get through all these questions. Okay, we will be back at 3:30, okay? Cool? So we'll take a 5 to 7-minute break. Okay, see you guys then. Okay. Alrighty then. Shall we get back to some math? Okay. So we've done integration. Integration's hard. It's not easy, but doing practice on very difficult questions can help. Okay. So that was what the previous bit was. Now we're going to go on to series. Series are also challenging, but in their own right, right? There are a few series tests. Same in the same vein of like us doing like an integral checklist. There's also a lot of like value in creating a series checklist. So that's what we're going to do right now. Series checklist. All right, and okay, yeah, you guys can see it. Series checklist. So let's make a list of all of our series tests that we've developed so far. Well, until the end of the course. What are some of your preliminary series tests? Okay, ratio test, AST, CT, or series. Anything else? Geometric series. Yeah, vanishing condition, which is divergence test. Divergence test, aka contrapositive of the vanishing. Contrapositive of vanishing condition. B-series test. Anything else? There's also one more, I think, that you guys missed. Harmonic series is not a test. It is a type of series. It's the name of a series, but it's not a test. What about LCT? GS is geometric series. And there's also one more that you guys are missing. AST is alternating series. Did you guys have the root test? Root test? Okay. I don't think you guys had the root test. You guys have IT? Yep. Integral test? And there's also good old-fashioned by definition. Yep, we mentioned vanishing condition. So we have a lot of series tests, a lot more than we had for integration. It's because series and knowing whether a series converges or diverges is a huge thing in the grand scheme of math. So we have a lot of tests to prove their convergence or divergence. Did I write down ratio test? I did. Okay. So your series checklist is going to be more so a list of signs to look for to know what test to use. Okay. So I'm going to actually make this list because we have a lot. Okay. What are let's go from bottom to top actually. Which tests do we never want to use? Which tests are like usually the worst to come up with? Using CT. Okay. I would argue that the worst test is actually by definition. Integral tests and CT are very useful actually. They come up a lot, but they're very specific in their use. I would say by definition. Imagine calculating the SN and then taking like evaluating, just finding a telescopic. I would hate doing that, right? I would hate taking the limit of SN. That's what by definition is. I would say AST is a lot to check. So I would say AST. Then I would say IT. I would say CT. Or actually, sorry, I should do LST or LCT, whatever. I don't use that very often. Limit comparison test is what it stands for. This is alternating series. This is on the last few pages of the lecture notes. This one's integral test. This one is comparison test. Then we have a few. P-series, divergence test, GS test, and then ratio test. Number one is definitely div test or divergence test. The reason I say it is because it's just checking the limit. Check the limit of your function. If the limit doesn't equal to 0, then it diverges. Super simple. I would go ratio test here, GS, and then P-series. Okay. I'm going to also include the kind of idea that the only two things that you can use to find what a series converges to is GS and by definition. These are the only ways to find what a series equals to. Right? We have discrete formulas for these, but we don't have, none of the other tests tell us anything about what the series equals to. We just know that it equals something. We don't know what it equals to. All right? Is that clear? So this is more so just a way to understand what the telltale signs are. This is if you can find ratio. If each term in your series is just a multiplication of a previous one by some number. P series is if you have something of the form like 1 over n to the p. Ratio test is when you have factorials or really funky powers. When you have factorials or really funky powers, this is what you want to do. Comparison test, if you really just, if you feel like you can bound it. If bounding it is easy. If you do integral test when you find that you could probably integrate it. Integrable. Like, does it look like something you can integrate? Like ln x over x, I could integrate that, right? And then you would use one of your integration techniques. So. AST. This is your alternating series test. And this is, again, if you have something that kind of oscillates. If it oscillates or it alternates between positive and negative values for each n, I would say do AST. Limit comparison, I actually don't find it very useful. I was always able to get by without using LCT at all. And then by definition is only useful when you have something telescopic. Something that when you expand it, you see that all the terms kind of cancel out. All right. Is this checklist kind of clear? Or clear for the most part? I know it's long. There's a lot of tests. But go through this like mental checklist. You should always associate a certain type of part. So like factorials, for example, that being your ratio test. Like you should always associate like these signs to use these tests and the test itself. Okay. Give me a thumbs up or a smiley face or something in the chat to say, hey, I got this. I know these tests. Right, cool. I like all the happy faces. Okay, seems like a good amount of you are okay. So now that we have this kind of checklist, we know what the signs are to use certain tests. What do you think we use in this case? For A. Yeah, ratio test. Why? We see a factorial. Great. I like that. So when you're doing ratio test, yeah, it contains a factorial. What we're going to be doing is we're calculating a limit. The limit in particular that we're calculating is we're just taking the ratio of two subsequent terms. This is all we're doing. Do algebra. We're going to do this one together. And then for the rest of them, the algebra is very, very easy. Okay. But just get the practice in with it. Okay. So an is n to the n over n factorial all squared. Okay. But an plus 1 is going to be wherever you see an n, replace it with n plus 1. So that's exactly what I'm going to do. And notice that I'm writing this as a division and not a fraction. Never, ever put fractions over fractions. You'll confuse yourself. If you feel comfortable with it, even like, even after like however long I've been doing math, I still don't feel completely comfortable in not doing this step. So this is a step that I've always been doing. I've never gotten rid of this step because I like when things look pretty and nice. I don't like when things look ugly. Okay, so now algebra, simplify. It's a limit calculation. You've always been taught to simplify first. So we're going to do that. N plus 1 times n plus 1 to the n over, can we agree that a factorial is just 1 times 2 times 3 times 4 times 5 all the way up until n plus 1? So this is the same thing as n plus 1 times n factorial all squared in our denominator, right? Cool. Then I'm going to turn this into the reciprocal. Real good with this algebra? Cool. Then cancel things. I see that this part cancels with this part. Anything else that cancels? There's one copy of the n plus 1 that cancels with this guy. So now what are we left with? N plus 1 to the n over n to the n. And then I'm going to put the 1 over n plus 1 on the side. Okay. All of these things are positive, so we can actually lift the absolute values. So now, this is what I feel like Poria may think of as a limit in disguise. Can we agree that this part of this thing, that could be written as something? In particular, it could be written as this. With a little bit of algebra, it turns into a super, super nice limit. This, if you notice, this is E. Do you guys remember this from 831? This guy's going to be times 0. So this is E times 0. What is that equal to? Lovely. Okay, so that means that L is equal to 0. What are we checking? We're checking if it's less than 1, greater than 1, So it diverges. No. This converges. Oh, wait, no. Wait, does it? If it's less than one, it's convergent, no? Yeah, it converges. Yeah, less than one converges. In fact, this means absolute convergence. This gives us absolute convergence. And absolute convergence implies convergence. Does that make sense? If it was greater than one, then it would be divergent. If it's equal to one, use another series test. It's inconclusive. In the conditional convergence, absolute convergence means that your series absolutely converges, right? So if you take the absolute value of your series, it's going to converge. That also means that your entire series is going to converge. Okay, it's going to converge for no matter what, even if you rearrange your elements. Let's just say that a series, it doesn't absolutely converge. You can't take the absolute value of it and get it to converge, but you can still get it to converge using another series test. That's what we call conditional convergence. And that basically just means that you can rearrange the elements, you can rearrange the order that you do the addition in, and you can get a different sum, a different final answer. Does that make sense? So just remember, ratio test gives you absolute convergence, and then you can use it to say it converges. Okay, the details matter here. All right. Are we good with that one? Self-explanatory, easy? Nope, not to the two. Not to the two, because the one cancels. Like this part, the two here cancels with this one. So it's just a one, right? Yeah. So yeah, algebra is hard. Algebra's not easy. It's algebra. Okay, this guy. What do you guys think? Go through your series test. Convergent by div test? CT? No. You see SN. Sine. Sine means UCT. Integral test, perhaps? I like the idea of using div test. Manu, you wanted to rewrite the thing, right? What if I rewrote AN as this? 1 over n over 1 over n. If I let x equal to 1 over n, exactly, the limit equals to 1 for this guy. And I'm going to show you why. Let's actually use theta in this case. I'm going to let theta equal to 1 over n. Okay. So I want to take the limits as an approaches to infinity, or an of as n approaches to infinity. So this is the same thing as saying limit of n approaches to infinity of sine 1 over n over 1 over n. Okay, cool. But I said 1 over n is equal to theta. So that means I'm doing the same thing as taking, when we say that n approaches to infinity, what does theta approach to as n approaches to infinity? 0. So now it's just sine of theta over theta. What is this limit equal to? Know your A31 limits. This does not equal to 0. Therefore, diverges by div test. This is a limit in disguise. I don't know about you. This seems like what I would think of it as a limit in disguise. Know your classic A31 limits. These are really important. Okay? So always check div test first. check div test. Even if you don't think it diverges, check div test. Because you may find that it does diverge. What about this guy? I did this in my series B during my very last tutorial. So for those of you who attended, this is a series. It's just written out in full. What is this equal to? This is geometric. Whenever you have something like this where it's written out in full, geometric. Find what the ratio is. What is R? Really quick way to find what R is going to be 1 over... Actually, no, this is not geometric. Not geometric. Even I forgot that this was not. Ooh, this one telescopes. And I'm going to show you why. I'm going to rewrite this part as 1 over 2 times 1 plus 1 over 2 times 3. 1 over 4 or 1 over 3 times 4. 1 over 4 times 5. What's the pattern? Yeah, it's only geometric when you multiply previous terms by some number, some constant number. If you get something like this where it's just written out, it's a sum that's written out, it's either geometric or telescopic. So what is this going to equal to if I were to rewrite it as like a sum? What would the general term be? Yeah, 1 over n times n plus 1. Okay. I'm going to put a quick note here. You can also use PFD on summands, on these guys. Do a PFD type thing. You're going to end up getting, after doing a PFD, that this equals to 1 over n minus 1 over n plus 1. You set it up in the exact same way. You do the n and then plus n plus 1, a, b, solve for when this equals to 1 over n times n plus 1. That's your PFD. A is going to equal to 1, b is going to equal to -1. You can pretty much just verify this just by plugging it in those values. And then cross multiplying. Cool? And then you would do by definition, no? You would find the limit as n goes to infinity, 1 over n, or 1 over 1 minus 1 over 2 plus 1 over 2 plus, sorry, minus 1 over 3. Yeah, partial fraction decomposition. Partial fraction decomposition is not just limited to integrals. Partial fraction decomposition is a technique to help us with integration, not necessarily the integration technique. PFD is just your backwards version. It's just going the other way when it comes to finding a common denominator. It's just the backwards of that. Right? Because essentially when you're doing this step right here, you have to find a common denominator anyway. But this is just breaking it apart into its original like rationals. Gonna keep going until 1 over n minus 1 over n plus 1. Right? Each of these guys is going to cancel with something. And what you're left with is the limit of 1 minus 1 over n plus 1, which is equal to 1. Does this make sense? Did I lose anyone? Yes? No? Maybe? Nuth, did I lose you? It's good? Okay. Looks good? Cool? I like that. All right. Not too bad, right? This one, always similarly to your integrals, always simplify your summand first. Always simplify the inside. This kind of like looks weird, right? It would be like it looks weird in particular because of the specific like it's n as the power and like some number as the base. It'd be really nice if we could get these to flip, right? You could do like a little swap. It's not going to be equivalent, but yeah. So remember how Fourier said to remember your like ln properties, your exponential properties? These are those. So we can actually rewrite this as if I take the e to the ln of 3 and then to the ln of n, that's the same thing, right? Where this is, yeah? Do you remember this rule? E to the ln of x is just equal to x. Yeah? Cool. Glad that at least one of you gets it. Cool. So now we can do some exponent laws. A base to a power is just you can multiply the powers, right? So e to the ln of 3 times ln of n. Okay, we can do this again. We can instead now choose to put the ln 3 on the outside, right? I could do e to the ln of n to the power of ln of 3. Can I not do that? And then after that, we can just remove the e to the ln. And would you look at that? I've exactly done what I wanted. I've swapped the n and the 3. Does that make sense? And then, yeah, it's a p series. It's a 1 over n. What is p? Ln 3. Cool. Okay, I'm going to do something really funky. Ln 3, that's going to be less than ln of e, right? How do we know? Ln is an increasing function. Ln is increasing on r, or on 0 to infinity. Yeah, and 3 is less than e. Perfect reasoning. Ln of e is equal to? No. Oh, wait, yeah, you're right, sorry. For some reason, I thought it was pi. I was like, yeah, 2.7-ish. It's bigger than 1. So what does that mean? P is bigger than 1, which means convergent. Are we good with this? Divergent. It's convergent. Yeah. The way you kind of know or understand, I don't memorize these things. I kind of just understand them. I know that 1 over n to the 1 is the threshold, right? So I know that that's like my harmonic series. I know that that diverges. Okay, but now I'm looking at why does that diverge? It's the tail elements still go to 0, but they don't go to 0 fast enough. AKA the denominators don't grow as fast as they need to make the entire thing converge. So I need those powers of n to be bigger than 1. So when p, or your powers of n, are bigger than 1, that's when it converges. I don't bother memorizing things in math. Okay, what about this guy? Yeah, you can do an alternating series test on this. Actually, no, you can't. Why can't you do AST? What are the conditions for AST? Sure, we have an alternating part. That's fine. But we need something else. This Bn has a condition. We need that the limit of Bn goes to 0. Does it? No, it's not even decreasing. We also need that it's decreasing, Bn decreasing. Can't do it. Okay, but sure, fine. Then maybe, so we don't have that Bn goes to 0. Okay. So what does this go to? Here's a little trick. If you find that a series, you feel like you want to use an alternating series test on it. If you find that the limit of Bn doesn't go to 0, check div test. Because if a part of your series, the limit doesn't go to 0, then what are the chances that adding an alternating part, it will go to 0, right? So check div test now. So if alternating series test fails, aka your limit doesn't equal to 0, check div test. What would be the limit of this? The limit of it would, yeah, it would diverge. It wouldn't exist. The limit does not exist. Does that equal to 0? Does this make sense to everyone? Is this kind of clear? Yeah. So when AST fails, we do div test. Okay. Okay, what about this guy? Okay. Why are we choosing to use CT? Why do we think CT? P-series? Lon is always small. Yeah, we can do kind of a manipulation kind of thing. We can, in particular, bound this by a really easy thing. Okay, first, okay, so we're using CT. Okay, let's try using CT. But when it comes to CT, we have to have a claim. We have to first decide, what are we trying to show? Are we going to try and show that it converges? So we try to find a bigger function, or do we want to find that it diverges? Try and find a smaller function. Could we really easily bound this from above by some function that we also know converges? Yeah. If I, so your kind of trick to use CT is if you covered up a certain part of your function, does it look like something that you could really easily find if it converges or diverges? Yeah, you guys are nailing it. You guys got 1 over n to the 2. Does that converge or diverge? It converges. Okay, so why don't we try and make our claim to be that try and find a convergent, so a bigger series. So our claim is that it converges. So let's try and bound this function, 1 over n squared ln of n. Okay, to bound from above, we need to maximize the numerator or minimize the denominator. Is there a way to do that? Can we minimize the denominator? Yeah. If you notice, n here starts at 3. If n is bigger than 3, then ln of n is also bigger than ln of 3. Ln of 3 we know to be bigger than ln of e, which is bigger than 1. This would be your train of thought. This would be your line of reasoning for this. So what it would be less than 1 over n times 1. And then it's a p series. So we would be able to say that the entire sum is less than this sum. And then by p series, this converges. Isn't that kind of cool? I create these questions very carefully, especially the questions where it has to do with a very specific trick, because I want you guys to be exposed to all these tricks before the final exam, if that makes sense. Okay, we're almost done the series portion of this. How do we feel about the previous question? This one. Very cool? Good with it? Maybe a thumbs up, smiley face, sad face even if you're not understanding something. Okay. Is that a good surprise or bad surprise? Good job, Lucas. Okay. In that case, next question. What about this one? It has a ln. It's to the power of n. We can't do a p-series thing on this because the power is not a number, it's n. What do we think is a GS? What's the number? What's the ratio if it's a GS? It has to be a constant as a ratio. It's exactly how I wrote it. It's not ln to the power of n of n. You can do CT. Okay, I think I created a question to stump you guys. Okay, I want you guys to know something. Again, bottom starting point is different. Maybe we can bound it, okay? Or you could do something like this. Rewrite it. Simplify your summand first. Hmm. Would you guys like it better if I did something like this? Oh my God, it's I know this mathematically doesn't make sense, but just to kind of help you guys. Does this look like something we can deal with? What if I did a, yeah, IT, not div test. Div test is going to fail here. The limit goes to 0 for this. We can integrate. If I take, let's just say u to be ln n, what's the derivative of ln n? 1 over n. Oh, I see it multiplied right there. Let's try and integrate this. There's a few steps that you need to do first when you try to integrate or convert something to an integral. You have to define a function of n to be an for all n in the natural numbers. This just makes sure that all of your natural numbers are covered by your function, because you can't integrate a discrete function. It has to be a continuous function of r. An is a function of n. Okay, now we have to do something. We have to check a few things. We have to check that our function is differentiable. We have to check differentiable, f. We have to check continuous. And we have to check decreasing and positive. It's a lot of things to check. The reason that IT is so low on my list is because, or it's one of the lower things on my list, is because of all the conditions you have to check. Well, my function, f of x, is going to equal to 1 over x ln x, right? Can we confirm that this is decreasing? I'm not going to convince you guys that it's decreasing. What you would do to show it's decreasing is figure out what the derivative is and then check that it's less than 0. Cool. Differentiability implies continuity, so we have that for free. We have decreasing, and then can we agree that this is positive? Let's do a quick sign check. Your domain, so on the domain is 2 to infinity, right? On 2 to infinity. This is going to be positive because ln of 2 is greater than ln of 1, which is 0. So the entire function is going to be positive. Okay, so we can integrate it. Now just integrate this. 1 over x ln x dx. You're going to find that this diverges. Cool? So this diverges, so that means that the series diverges. But I'm not going to go through the process of integrating that because it's pretty simple to integrate. This is just a u sub. So we showed the integral equivalent of it diverges, exactly. That's another property we can kind of rewrite like that. What do you mean, property? They're not equal, but when the integral converges, the series will converge. When the series diverges, the integral will diverge. It's an if and only if for the divergence convergence part. Oh, that's another ln property, yes. So do you guys remember the ln of a to the x is equal to x ln of a? You guys remember that? It's like your power rule. You can bring down the power. One of the first things from high school you learn, or first important things from high school you learn. Yeah, so just be aware of all your ln properties for this one. Okay, what about this one? AST. What told you that it was AST? Oscillating, good. Is there a way you can simplify it? Yeah, it's the equivalent of writing the -1 to the n. You can always rewrite it, right? Whenever you have a cos pi k or a cos, or sorry, this should be an n. Whenever you have like a sine n pi over 2, you immediately oscillating, alternating. you're oscillating kind of sequences from the sequence part. If you put them in a series, they're also going to be oscillating, obviously. Okay, so now what do we need to check? We need to check decreasing, right? The rest of the part, we need to check that the rest of it is decreasing. We need to check that, so we're going to call that BN, BN decreasing. We also need to check that BN is positive, and BN goes to 0 as n goes to infinity. You will find that all those things are true, so this one actually converges. Are we good with this? Again, the way that you would show decrease, BN has to be positive. Yes, I believe so at least. That would be something good to check. That's something I probably should know. I believe it has to be positive. The way that you would show it's decreasing, for example, is like you wanted to show that B of n is greater than B of n plus 1. So you would just, from the ground up, you know that n is less than n plus 1. Take the square root of both sides. Because square root function is increasing, we can do this. Then reciprocal. So it's a power series with... this is not a power series. This is not a power series. A power series has x in it. This is not a power series. Yeah, power series rely on x. It's an x minus a to the power of some n, right? It's an x minus a to the power of n times some series or some sequence kind of term. Okay. We're almost near the end, guys. I just have a few more questions. These are the short answer, but hard questions. Short answer. Okay. This one is a little bit of like an out of the box kind of thinking question. This one is all pure algebra. Okay. I'm actually very curious to see if you guys kind of know what to do for this. So for this question, it's asking find all values of the constant b in the real numbers that are positive for which the following series converges. So we essentially want to find a interval of convergence, quote unquote, right? It's not an actual interval of convergence, but it's just the values of b, right? So an interval where this series converges. Okay? This is not a power series. How would we go about this? Well, does this kind of look familiar? We kind of had something like this before, right? Where it was some number to the power of ln to the n. What do you think we're going to do? Exactly. We're going to turn it into an exponential kind of form and then rewrite it as like a power series, or sorry, a p series. So let's do that. E to the ln of b. So I'm going to actually write this from the ground up. B to the ln of n is the same thing as e to the ln of b of ln n. Then we're going to use exponent laws, ln b, ln n. Keep it going. E to the ln of n to the power of ln b. Yeah, you should have got it. This is going to be an n to the ln of b. But this is not in a denominator. We want it to be in a denominator, so we could just do this. Negative ln b. Can we agree that these two are equal? Okay, but this only converges when negative ln of b is equal to p, when this is greater than 1. When is this going to be greater than 1? when ln of b is less than -1. And then we can take the e to the ln b, e to the -1. And then this is just going to be b is less than 1 over e. So what interval is b supposed to be in for this to converge? Well, Kishan got it, so this. Because we're only looking at positive real numbers, right? B is a positive real number. So this is our final answer. How is this kind of question? Is it okay? Decent? Good even? Cool. Now, is it 0 or 1 since n equals 1 in our series? N equals 1, sure, but b is a positive real number. So b and n don't connect to each other at all. Yeah. Okay. Normally I like yapping, but this is like 3.5 hours of solid yapping. So I'm like, my throat is like angry at me. Okay, this question. Remember how I said that there's probably gonna be a question where you have to find the interval of convergence for a power series. Okay. How do we know this is a power series? Let's identify a few things. There's an x in there. Okay. Can you tell me what a is? What is a equal to? 1. It's not -1, it's just 1 because we want something of x minus a. Okay. What is our Cn? What's the remaining part of it? Yeah. Okay. I'm going to tell you right now. Whenever it comes to finding an interval of convergence, it's the same procedure every time. Always do a ratio test. Always. Ratio test is the actual, like the best tool when it comes to this. Because it tells you absolute convergence as well as just convergence, right? It tells you a lot more, gives you a lot more info. And it also gives you your R. So when it comes to the ratio test, you're just doing the same thing, finding the limit as n goes to infinity of the entire thing, including the x minus a to the n part. So you're going to do an plus 1 all over an, and then just plug things in. N goes to infinity of the interior, including the x part. And then again, keep it simple. When does the seminar finish? We're going to try and aim for 5 o'clock. It's been like 3.5 hours. Then we're going to do the same thing. And on. And limit as n goes to infinity. We're going to cancel some things. We're going to end up getting x minus 1. And then it'll be n plus 1 ln n plus 1. Notice that we're starting at 3, so we're positive. Ln is always positive, so I can just remove the absolute values for that one. And then it's going to be n root ln n over 1. Well, so now I'm going to remove the x minus 1 because the x minus 1 is not dependent on n. Right? Now, how would I calculate this limit? It's a really ugly limit, but what would it be? So the absolute values have to stay around the x. They came from the actual like definition, right? We can take the absolute value of the ratio. Yeah. So because the absolute value of x, we can't guarantee that that's always positive, right? So we have to keep the absolute values there. But what does this limit equal to? What do you guys think? You can do some lawn properties if you want, some like implicit L'Hopital's rule almost. It's gonna go to 1, right? That times 1 is just equal to this. Okay, now question, when does this converge again? For what values, like what does this need to be for it to converge? We need it to be less than something, less than 1. So now we have an interval almost. X minus 1 has to be less than or in between 1 and -1, right? So where does X have to be? X has to be between 0 and 2. But this isn't enough. We can't just say this. We're missing information. Remember how in the true, yeah, check the endpoints. Remember how in the example, in the true and false example, we knew that it converged at 4, but we didn't know anything about -4? We have to check the endpoints. So let's do that. So what you do to check the endpoints is literally just plug in your values of x into your original function. So I'm going to plug in x equals 0. So when x equals 0, we have, what was it? It was 0 minus 1 to the n over n ln n. How do we know? Because this, so the ratio test tells you that this converges when it's less than 1, when your limit is less than 1, right? Yeah. So we're just using that fact. The reason that ratio test is useful for these kinds of questions is because it gives you an absolute value. An absolute value can be unraveled to give you an interval. How would you test this one? The same thing as? That's at 3. -1 to the n over n root ln n AST. Yeah, this one's an AST. And it converges. What would you do for checking negative or 2? You just plug in 2, right? So it would be 2 minus 1 to the n over n ln n equals 3. This is the same thing as n equals 3 n ln n. This is going to be 1 to the n, which is just 1. Yeah. By CT gets us to diverge. CT divergent. So your final interval of convergence is 0 to 2, excluding 2, but including 0. So whenever x is a value that's between these two numbers, you're going to get that the series converges. Cool? Is this pretty straightforward for the most part? Give me a thumbs up if you feel like this question's okay. Or this type of question is okay. You'll see, Anjali. Yeah, Lucas finds it okay, and Chen. You're not aware of how to compute the limit? Okay. The limit, you can kind of do a L'Hopital's rule kind of thing. It's not actually L'Hopital's rule, but so L'Hopital's rule only works with continuous functions, right? You need to be able to differentiate the numerator, differentiate the denominator. This one is a discrete function. You're not allowed to differentiate discrete functions. But you can kind of still use the same intuition behind it. Differentiate the top function, differentiate the bottom, see what you get. That limit is going to be equal to the original limit. So refer to like L'Hopital's rule almost. L'Hopital's in hard quotes. Yeah. Does that make sense, Benedict? Cool about that? Everything else okay though? Kind of question the easy now? Okay. All right. This is my last official question, okay? This is my very last official question. It's a long paragraph, but trust me, it is easy, okay? It's just a fun question. I thought would be cool. Kathleen put this on like an extra exercise last semester, and I really liked it, so I stole it. Don't tell her I said that, but okay. An infinite number of mathematicians walk into a bar. The first one asks the bartender for a beer. The second mathematician asks for half a beer. The third one points to the second mathematician and says, "I'll have a fourth of a beer." The bartender interrupts and says, "You're all idiots. You guys need to learn your limits." Then places 2 beers on the beer stand or on the bar stand. Provide a mathematical explanation for the bartender's response. That is, how exactly did he correctly know that he had to serve exactly 2 beers to satisfy the request? Anjali got it. Anthony, I like that thank you for enjoying this question. Not a harmonic series, not a harmonic series. You guys are funny. It is 1/2 to the power of n. That is what your series looks like. Notice it's 1 plus 1/2 plus 1/4. What do you think the next one's going to be? Plus 1/16. Or sorry, not 1/16, 1/8, and then keeps going. It's going to be 1/2 to the power. No, you're right. It's 1/16. What was I thinking? It's 1/2 to the power of n. What is your ratio? 1/2. Absolute value of the ratio is less than 1, therefore converges. And we know what it converges to. It's not negative 1/12. It is 1/8? Is it 1/2 to the power of 4? Is it? Hold on. It's 1/. Oh, right. Sorry. It's been a long day. I've done too much math today. But regardless, it's this series, 1/2 to the power of n. So converges. And then your first term is, yeah, you're right, Anthony. 1 minus 1/2, right? And then this equals 2. Exactly. This would be sufficient to give for this question. I think that this is a really fun question. It gets you to think about math in the context of not math. Okay, that was my very last official question. And luckily we did end in before 5, which is what kind of my goal was. But there is a very last bonus question that I want to do with you guys. Do you guys think that you want to see this? Because this may boggle your mind. It may keep you flabbergasted. It may, uh, you know, knock your socks off and other vernacular. Okay. Drive you insane. Yes. This is a really cool question that I do every single review seminar for A37. Thanks, Anjali. Okay, here is the question. Show that the following series evaluates to 2. It seems pretty self-explanatory. It's not. This one, you can't really do any series tests to it. You can't, it doesn't diverge because the question literally tells you it converges. It converges to 2. It's not geometric series, so you can't use that. The only way to go about this is by definition. So to term by term, expand this guy, because no other series test can tell you what it evaluates to, right? So we only have 2 tests. We only have 2 things to do here. What I'm going to do is I'm going to write Dave in full. I'm going to do term by term expansion for this guy. First term, 1 over 2. Second term, 2 over 2 to the 2. Plus 3 over 2 to the 3. Plus 4 over 2 to the 4. Keep going. Next, I'm going to split each of these fractions, specifically like this. And so on. Can we agree that I can do this? This is a valid move. I can do this. And keep doing it indefinitely. Cool. Now I'm going to split these guys. 1 over 2 to the 2 plus 1 over 2 to the 2 plus 1 over 2 to the 3 plus 2 over 2 to the 3 plus 1 over 2 to the 4 plus 3 over 2 to the 4. And then keep going. I want you to notice something. This guy, this guy, this guy, this guy. Can we write him as a sum? What can we write him as? How about a little this? You should have got it. But let's see the magic at work. I'm still gonna write these guys. This is a geometric series. We know what he equals to. He equals to his first term, so 1 over 2 over 1 minus the ratio, which is 1 over 2. 1 over 2 is less than 1, so we can still say that this converges. So this part is going to be 1, right? The rest of it, though, let's factor out a 1 over 2 from all of it. So what do we end up getting? 1 over 2 to the 1 plus 2 over 2 to the 2 plus 3 over 2 to the 3 plus so on. Do you notice what this thing is? What is this? There's a reason I gave him a name. He's that special. And his name is Dave. So we have 1 plus 1/2 times Dave. I just made Dave show up again. So this is Dave is equal to 1 plus 1/2 of Dave. Let's isolate for Dave. So Dave minus half of Dave is equal to 1, which means that Dave over 2 is equal to 1, which means that Dave equals to 2. Did you guys like that? This is why I love series. Series are so cool because you can do things like this. And this one is perfectly mathematically valid because this actually absolutely converges. This series absolutely converges. And this is a valid thing that you can do. So no matter what you do with Dave, he's 2. He's equal to 2. So if you see n over 2 to the n, this is what you do. Don't memorize it, understand it. Okay? This is just a bunch of algebra and like arithmetic tricks to get what you want. All right. But with that, what if the base was 3? If the base was 3, it wouldn't work exactly the same way. But it's I mean, it's valid to check. Actually, if the base was 3, it wouldn't equal to something, it would equal to something different. I think it would still converge, but it would just be something different. It could be like 3 or something. Yeah, it's more than like, I would highly recommend trying it for yourself. That's actually a good question. Try it with the base of 3. See if this kind of trick works. Okay, but with that, thank you guys so much for attending the review seminar. We lost a few members on the way, but for those of you who stuck around for the full 4 hours, thank you for giving me your undivided attention. I hope this was helpful. And I will still have office hours tomorrow morning at 11. So if you want to show up, feel free. We'll also probably be invigilating. So you'll see me in the exam room. If you want to say hi, say hi. If not, I'll just see you there. And yeah, with that, good luck on your final exam. I will try to post this as soon as I get the recording up. But with that, I'll see you at the final exam. Bye, guys. Bye.